I'm going to welcome you all to tonight's meeting of the Hertford Astronomy Group. It's lovely to see you, whether you're a newcomer or a regular visitor. We are absolutely pleased and thrilled to see you. We've got 75 people in our meeting tonight, and I think that's terrific. Permit me to introduce myself to those of you who don't know me. I'm Alan Willison. I'm the chairman of the Hertford Astronomy Group. This evening, we're going to hear about forthcoming items of interest in the night sky from Martin Weston. Following that, Jerry Stone, our programme secretary, will introduce tonight's guest speaker. And we're privileged to have George Tahu from NASA with us this evening. Jerry will tell you more about George in his introduction. After the talk, I will be closing the meeting after giving you some insight into next month's meeting. Tonight's meeting is being recorded with the permission of our speaker and will be made available on YouTube by Saturday, hopefully. A link to the recording will be posted on the club website, heartsastro.org.uk, when it's ready. Links to previous meetings which have been recorded can also be found on the website. As a courtesy to our speakers and fellow guests, your microphones have been muted so as not to cause unexpected interruptions. So it's with great pleasure I pass you over to Martin.
Can you hear me okay?
Yes, we can hear you.
Good. Okay, let's see if I can get my screen share working. There we go. Okay, everybody, welcome. I'm going to give a little talk about March and what we could possibly see in the sky if we get some clear evenings, which we haven't had recently, unfortunately. Well, we've had a few clear nights where we've managed to get out and see a few things. I do hope that the items of interest that I spoke about last month, you did get a chance to see some of those. So I'm hoping that the ones I'm going to give you this evening, you do get an opportunity to look at those as well. But so this week at the moment, we seem to have clouds and rain. So all we can do is hope for clear skies. So the first one I'll talk about is an old moon, which ends tomorrow. So here I've just got a picture of as it disappears. It'll be pre-dawn, bright planets on that day. Will be Mercury, Jupiter, and Saturn here, in the southeast roughly. So anybody up early in the morning? So it's getting lighter in the mornings now, I notice. So it'll have to be probably 5-ish or 4-ish to actually catch this. But Saturn's quite faint at the moment. They do form a sort of a row. And there's the moon down here. So we're going to, that is the, say the old moon for this month. We'll move on to Tuesday the 16th. And we get the new moon. It's a crescent moon and it's very close to Uranus. I spoke a little bit about Uranus last month. Again, you can see it through binoculars, or if you know where you're looking, it's a sort of a pale greeny blue colour, but it is quite small, but you can make it out. But if you look here on this picture, you'll see the moon here, and Uranus just above, almost sort of from the moon up at 45 degrees. In Aries, yes, in Aries. So I've just put a little bit of information there. The western sky on Tuesday evening, young crescent moon. It's saying it's several fingers width, 3.5 degrees, south to west, in Uranus. So with binoculars, you can make it out. It's quite nice to see that through a small telescope or binoculars. We'll move on to Friday, and we're looking at the moon again. It's a good reference point, the moon, to find things when it's close to some of the planets, but it's close to Mars on Friday, the 19th of March. It's not as bright as it was last year when it was very close, as it's on the other side of its orbit now, so some distance away, but still nice to pick out. Its colour gives it away, and it's always good to know where the planets are at any one time in the month. So if I move on to the next, we come to the equinox, which is on the 20th of March. And this is when the sun will cross the celestial equator, traveling north. And we get equal day and night. And it's worth just mentioning at this point that the clocks will go forward on I think it's the 28th of March, 1 o'clock in the morning. So we'll get even lighter nights then, and it means that if you want to do any observing, you're gonna have to wait a little bit longer before it gets dark enough to see anything, unfortunately. But it does mean when we're outside, as the sun comes, that it's warmer and we can stay out longer without having to wear stacks of clothing to keep ourselves warm. I'll move on again to the 21st, and took it showing the moon at half phase here. It's also talking about an interesting cluster, the M35, which is a beautiful cluster. You can see it in the dark skies area, you can see it with the naked eye, but through a pair of binoculars, it's a beautiful sight. So I do advise anybody to look at these clusters if they possibly can. If you've got a copy of Stellarium, that marks all the clusters beautifully on there, and it does make it a lot easier to find them in the sky. But this particular one, I've got a picture, not one of mine, but this picture I took off the internet of M35, and it's beautiful, sparkling cluster of stars of slightly different colours, blues and yellows. So if it's clear night, or any night really, because it's quite high at the moment and easy to find, then I would advise you to have a look at that. Very pretty. We've got one comet at the moment, Tempe Temple, which is going to reach perihelion on the 24th of March. Unfortunately, it's too far away to see without quite a powerful telescope, and you need to know where it is. But as it comes round in November, it will be a lot closer to us, 1.6 AU, which an AU, for anybody who doesn't know, is the distance from the Earth to the Sun, the average distance, because obviously that varies as we go around. So that's 1.5 times the distance that we are from the Sun away from us, and we should be able to spot that with binoculars and telescopes. Another interesting star constellation to look at this time of year is the twins Gemini, because they're very high up, and the two main stars in that are Castor and Pollux, and they are quite interesting stars to look at, especially through binoculars. You can actually see that Castor is actually a double star, and you can actually separate the stars out with a telescope. Quite not so easy with the naked eye, but they're quite easy to spot because they're quite bright stars and they're high in the sky at the moment. So definitely worth a look. So on the 28th of March, we've got a full moon. This is known as a worm moon, or a crow moon, a sat moon. I don't know what all those mean or why they got those names, but they've got various names. But the moon at this time, you know, when it's full like this, although it's difficult to look at because it can be quite bright, But when your eyes actually get used to the brightness of it, you can make an awful lot of detail. You can see here quite a bit of text. You can see the craters. You can see the smoother areas, the seas, all the mares. Always, if you're a new observer and you've just bought a telescope, the moon is a very good thing to start observing because it's fairly easy to find. It gives you a chance to test your telescope out and to practice focusing and following it using the controls to maneuver your telescope to track it. So yeah. So Venus is at its brightest on the 28th also, only in the morning. So this is a morning shot. But Venus is one of the brightest objects, nighttime objects, although it is partially visible during the day because it's within our orbit and it's closer to the sun. But it's a beautiful bright object to see, and that's a lovely picture I borrowed from the internet. And you can see Venus through, although it's quite light. Nothing else to talk about. Last month I was talking about when we observe things in the sky, how we see pictures of these things and we imagine them to be big and bright and easy to see. Well, I thought just to give you an idea of what we're looking at sometimes and trying to find things, this was an object that I was looking at the other day because some of the more interesting objects are dropping below the horizon now. So anything that's near the pole star or near the northern end tends to stay in view for quite some time because the rotation of the Earth leaves them in view quite a lot of the night. So decided to go for an object that was quite difficult, quite small object, which is Messier's 76, which is also known as the Little Barbell Nebula or the Cork Nebula, and it's located near. This is Cassiope standing on its side here, and you've got the Andromeda Galaxy down here, and in the middle here is this little tiny planetary nebula. But what I've done, I've taken, that's an image from Stellarium. But this image I took on my 71mm telescope, which is quite a wide field telescope. And it just shows you the amount of stars that are in the sky. I mean, if you looked at this area, you'd be lucky to see 3 or 4 stars with your eyes. But using a camera here, you can see the millions of stars. But this little nebula, this little planetary nebula in the middle here. You can just about make it out in the image. So I also took another image with a more powerful telescope. So as you can actually see the shape of it here now, it's a planetary nebula is a star like our sun that's reached the end of its life, and it's expelled all its material out, and then it's shrunk to a white dwarf, and the white dwarf lights up all the material that's been expelled. So the last picture is I stole off the internet just to show you what it looks like with a really big telescope. You know, I think that was taken in the Atacama Desert. But you can see here at the center, it might possibly be this star here, which is actually lighting up the whole nebula. It's actually a white dwarf. And this is all the material that has been thrown off. And depending on what palette they've used for the picture, potentially this is oxygen and this is hydrogen here, the red areas. But it just gives you an idea of how big these telescopes and how much magnification they can produce for that little dot that we were looking at to begin with. And that concludes my tour of the sky for March.
Well, thank you very much indeed, Martin. Really fascinating things there. There were lots of comments coming up about how beautiful those photographs are. And you are one of our club's real ace photographers, aren't you? You've got some terrific equipment there. We've got several people in our club who are brilliant at taking photographs. And remember, they were all beginners once. So if you're interested in learning how to take a beautiful photograph, we've got people here who can lead you by the hand and get you taking some of those lovely images. So once again, Martin, thank you very much indeed for preparing the talk and those super images that you put up there. We now move on to the next part of our meeting, where I'm going to hand over to Jerry Stone, who's going to introduce tonight's speaker. So over to you, Jerry.
Thank you very much, Alan. Some of us were talking earlier on about this being about the anniversary of COVID. And certainly it's been a year incredibly different from anything that we would have foreseen this time in 2020. It's, for many of us, I'm sure, it's not been a period that we would have liked to have gone through. I mean, I've had various problems myself, which some of you know something about, but through it all, I've always tried to keep myself involved in things, and my hobbies, particularly astronomy and space, have really helped to keep me sane. It has to be said. And although I've been sometimes in solitary in the care home, or as I am at the moment by myself in a hotel room, I've still been able to soar outwards and explore the moon, planets, stars, and beyond. And this is something I think that's basic in all of us. That we want to know, what is there over the next hill and beyond? And in my lifetime, we've taken it far, far beyond that. And we are physically, although robotically, it's not us yet, exploring all over the solar system. And it's really an incredible adventure. And so I'm absolutely delighted to be able to welcome someone to talk about the very latest mission by NASA to Mars. And especially as he is the lead program executive for the Mars 2020 mission. He's also the deputy director of NASA's Mars exploration program. So not just this mission, but the whole program of exploring Mars. So we couldn't really ask for anyone with more authority on the subject. And so will you please welcome George Tahu from NASA headquarters. Over to you, George.
Good evening, everyone. Are you able to hear me okay? First. The audio is good?
Yeah, we can hear you, George.
Great. Yeah, and thank you so much for inviting me to join your group and talk a little bit about Mars 2020 mission and broadly what we're doing exploring Mars. I do have a presentation that I'd like to go through. Mostly it's pictures and images I'll be talking to, but as we go along, you know, we can have some Q&A time at the end. But absolutely, if as I'm talking, you know, I'd certainly enjoy having, you know, back and forth engagement. Since we do want to keep muted, maybe if I could ask, you know, you could pose some questions in the chat, and then maybe Jerry or Alan, you can, if you see one that, you know, is particularly appropriate or is good to break in, please do, and I'll try to answer briefly, and then we'll cover whatever else towards the end. So I will, yeah, before I get the slides up, yeah, I've been at NASA about 20 years. I joined in 2000 after spending, I kind of wrote this in the chat, but had spent a few other years in private space industry before I came to NASA, and joined the Mars exploration program really as it was as a result of failures. Quite honestly, we had had two mission failures in '98, and we needed to kind of relook and restart the program. And the program director at the time was putting together a new team to help put that together, and I was part of that group that came in. And that year we spent a lot of time working not just within NASA, but our international partners broadly, because we view, Mars exploration as a worldwide effort. And so we put together a long-term program based on a set of overarching science goals. And we talk about four main science goals for Mars exploration. Kind of the first among equals is that question of, is there life beyond Earth? Could there be life or have been life in the ancient past on Mars? And part of the ways we try to understand that is by studying the geology. That's another goal of the planet, studying its ancient climate and current climate and how that's evolved over time. And then the fourth big goal is, so far we've only been able to send robots, and someday we'd like to be able to visit ourselves as humans. And so we want to do as much as we can to prepare for future human exploration. So all the robotic missions that we've been sending for the past couple of decades been focused on, one or several of those goals. And they've all been building upon each other, both scientifically and with the technological capabilities that we go. So, every mission is standing on the shoulders of giants that came before the prior mission. And here we are at that time in 2000. In fact, we thought we were on the cusp of doing a Mars sample return. In fact, that was some of the initial next missions we were going to try to do. But we realized we really weren't ready to do that. And it took a lot more for us to learn both scientifically and technologically to do so. But now's the time. And so we have now, Mars 2020 and the Perseverance rover is the beginning of the first round trip to Mars. This is starting what we call the Mars Sample Return Campaign. And it's something that we're doing in very close partnership with the European Space Agency. Our mission, this first one, is that first leg. Then there will be two other missions. So actually, I'll start to get into my pictures now. I can pull up my share. All right. Can you see my title slide?
Yep, that's fine.
Okay, good. And you still see my video, is that correct?
Yes, that's correct.
Great. So with all the missions that we've been sending, we recognize now Mars today is a very cold, dry desert. This is a picture from the Curiosity rover, which launched in 2011, landed in 2012, and has been roving at a place called Gale Crater ever since. But from all these missions that we've been sending, both NASA and international missions, the picture that the science teams have put together is that a long time ago, 3.5 billion years ago, Earth and Mars were very similar. They had a very similar birth history, right? And when the solar system was forming, all the gas and dust swirling around and coming together to create the planets. About that time, we believe that Mars had a much warmer, wetter environment and as well as a thicker atmosphere that potentially could have been a habitable environment. So that raises the question. At this point in time on Earth, 3.5 billion years ago, that's when we started to see microbial life start to evolve. So if the conditions were similar on both planets, could life have arose on Mars at that time period? So I mentioned the many missions that we've sent over the past couple of decades. This is a smattering of kind of the Martian left-hand side of this graphic is the Martian fleet that's already there at Mars. Several NASA orbiters, European orbiters. Now, just this year, same time we landed with Perseverance, the United Arab Emirates Hope orbiter has arrived, as well as China's Tianwen-1 has reached orbit. So there's quite a lot of capability, and these are just the ones orbiting. There have been some prior missions that have already finished their lifetime, like the Spirit and Opportunity rovers and the Phoenix lander that we sent to the Northern Pole. And there's several coming up. Certainly the next step after this year is going to be the ESA ExoMars rover, the Rosalind Franklin rover. And then, Japan is planning an orbiter to send, and then this sample return campaign I'm talking about. So all of these missions have been building on, like I talked about, the science knowledge. First, we started with a theme called Follow the Water. Was there water on Mars? What did that mean to the evolution of the planet? And then asking that question, well, did that mean that there were the right conditions for potential life to evolve? That's exploring habitability. And the answer to those questions was yes, indeed, there was. So now we're ready to actually go to the surface and try to actively seek signs of ancient life. So this Mars sample return campaign I discussed, this 3-part program, we're starting with Perseverance, then a joint mission between NASA and ESA is to send what we call the retrieval mission. Perseverance will collect the samples, and then this Fetch rover, which would be built by ESA, landed on a lander with a small rocket that NASA's would contribute. The Fetch rover would pick up the sample tubes, and what we're talking about are sample tubes. This is a model about the size of what the sample tubes are, and it can fit a sample about the size of maybe a chalkboard piece of chalk. And we seal them up, hermetically seal them, leave them on the surface for this retrieval mission to come pick them up. Those sample tubes would be put into a canister about the size of a basketball, volleyball, and launched into Martian orbit. And then the third piece is the orbiter. This would be largely built by the European Space Agency with the sample capture and containment components provided by NASA. And this orbiter would then use solar electric propulsion to spiral out of Mars orbit, return to Earth, release the Earth entry vehicle, and the samples would land in the Utah desert. So this is our grand plan for the coming decade. Coming back to that question of a habitable environment, here's a photo of the Gale crater, which is where Curiosity landed. And that's what Curiosity was trying to answer that question. Were those conditions for life present on the surface of Mars? And it did indeed find that, at least at Gale crater, that indeed was the case. It had the records in the rocks were able to tell us that at one time Mars had the right chemicals and enough water was flowing over a very long period of time, and there was enough energy in the system to at least potentially support life as we know it here on Earth. So what type of life signatures are we looking for? It's not going to be these macro fossils that like we might normally find when we go back to the stream or the outcrop in our own backyard, like fish or plants. That's not what we're looking for. What we are looking for are evidence of these microbial types of colonies. And on the right-hand side is a picture of some structures that you can find in the Australian outback, 3.6 billion years old. These are structures called stromatolites. And microbial mats build up and over time compress, and as they dry out and fossilize, create these rocks with these wavy and layered patterns. So it's these types of things that, if the science team could find this, that would be absolutely the holy grail. But we may not actually find something so obvious, right? So what we need to do is send a spacecraft that can look for what the team is calling potential biosignatures, be it chemicals, mineralogical signatures, maybe organic molecules, or even the shape and pattern, the morphology of the rocks themselves that would be indicators of something that a biology might have left, a biological process might have left behind. So we can launch to Mars. We try to launch to Mars about every 2 years. Those what we call a launch opportunity. That's when Earth and Mars, of course, in their orbits around the sun are closest together. We launched in July last summer, July 30th. And this represents the trajectory that we had to take. You know, you can't aim straight at Mars. You have to aim where Mars is going to be, kind of like a American football player throws a football to the receiver down the field. That's how we have to do our trajectory. And then, of course, the spacecraft meets up with Mars at the right point, and then we have our landing. Over the years, we've definitely been evolving our capabilities. The very first rover we ever sent was a technology demonstration on the 1996 Mars Pathfinder mission, the Sojourner rover. And then that was the first time we ever roved on Mars. So we realized, yes, this will work. This type of mobility system can work. And then we took it the next step with the Spirit and Opportunity rovers, launching in 2003 and landing in January of 2004. Then we realized we really needed something much more capable to seek to go to this question of searching for habitability, and that was the Curiosity rover. So we utilize the same design. If you look at Curiosity and Perseverance next to each other, you know, for first glance, they'll look almost identical because we built on that same common design. But there's many different things improved and advanced on Perseverance and some different things under the hood. Just a few quick things. The wheels, we redesigned the wheels a little bit differently. The turret on the end of the robotic arm, Perseverance's is quite a bit larger. It weighs about 100 pounds here on Earth, and has a different type of drill, a rotary percussive coring drill, as opposed to the drill that pulls up powdered samples on Curiosity. And then, of course, some of the other science instruments are quite different. So I talked about the overall big program goals. You can see a parallel with the specific goals for our mission with Perseverance. In order to get samples that have the best chance of having an indication of potential ancient life, we need to understand the context of the geology so that the science team can then narrow in and pick the right rocks to use the what we call the contact instruments on the end of the robotic arm to seek out some of those potential biosignatures. And then, of course, do the drilling, cache them in these tubes, leaving them on the surface. And I mentioned the other big objective we have, preparing for humans. You don't get to go to Mars that often. So anytime you do, you want to maximize what you're going to get out of it. When we started designing this mission, we put out an open call for the science instrumentation and investigations we could do. And while a lot of that was focused on this, you know, seeking signs of life, we also worked with our friends in the human spaceflight community and said, what are your top priorities if you could send something on this rover, something that fit within the constraints we had? And they came up with a list. And so we actually have a couple of instruments and technologies demonstrations on the rover to support future humans, exploration and designing those systems. And the whole launch sequence and everything else I mentioned, virtually the launch, the cruise approach, and the entry, descent, and landing technique, identical virtually to what we did for Curiosity. So here's a artist drawing of our rover. I mentioned the science instruments. We have 7 investigation instruments on board. I'll kind of starting from the top and kind of working down. At the top of what we call the mast, with that head looking thing on the top, is where we have our context instruments. Mastcam Z, those are our main eyes, the big cameras. So most of the great imagery you've been seeing has been, much of that has been coming from Mastcam. And then also the SuperCam instrument. Both of these are next generation versions of what is on Curiosity. And SuperCam is a joint collaboration between Los Alamos National Labs here in the US and the French Space Agency. Big contribution from CNES. Then on the mast and a little bit other places on the rover, we have several sensors for a weather station, the META instrumentation. This is provided by Spain. And this is also a next-gen version of what's on Curiosity, as well as the InSight lander. There was a version of this landed. And this helps us get wind and temperature, pressure, and there's also a camera to look up in the sky and monitor the dust environment and some radiation. So it gives us an overall understanding of the weather and environment. Then within the body of the rover, we have first ever ground penetrating radar that's provided by Norway. And so this is the first time we've ever had that at a surface level. We've had radars observing Mars from orbit, but now we're able to have this ground truth and really penetrate several meters down below. So that's going to be exciting. And then the other interior instrument we have is MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. And this is that preparing for humans. So this is an instrument about the size of an automotive battery that would suck in the atmosphere of Mars, which is 96% carbon dioxide, heats it up, pumps it across a catalyst, and splits it in two, into carbon monoxide and oxygen. And we can measure the purity and amount, the flow of the oxygen coming out. And the whole idea is that this is a prototype of a technology that could be scaled up so that when we eventually send future humans to Mars, we can generate the oxygen on the surface, living off the land, rather than bringing all the oxygen we might need for breathing and for return propellant, for rocket propellant. Rather than bring it all with us, we can generate it there on the surface. Then out on the end of the arm is the two contact instruments, Sherlock and Pixel. Sherlock is a ultraviolet laser spectrometer and can detect mineralogy and organic molecules. This is some of the first time we'll be able to get high resolution of organic molecules. And of course, if you have Sherlock, you got to have Watson to go along with it. It's the small camera, a high resolution camera to really get good images. I have to hand it to the JPL team figuring out an acronym that spelled out Watson. I can't even remember what it was. It was quite contorted, but it went with Sherlock. And then, of course, Pixel, an X-ray spectrometer, largely focused on understanding the chemical makeup of the samples. And in between those two is the big rotary percussive coring drill. And this drill is, if you can see, this is a 3D print model of the coring drill bit. You can see it's hollow inside. And we take a tube is inserted into the drill bit. So when we drill into the rock, that core is put directly into the sample tube. Then the robotic arm docks it to the front of the rover. You'll see that sort of round thing on the front there. We call that the carousel. Releases the drill bit, then it's rotated around. So now this drill bit is on the inside of the rover. There's a smaller robotic arm inside. You can kind of see it on the left-hand image there. And that pulls out this tube out of the drill bit, maneuvers it to the sealing station. We plug it up, hermetically seal it, and then we have a choice. We can put it back in the storage rack, which we probably do, and await the time until we're ready to drop it on the surface at the location that we want to leave the samples for the fetch rover to come pick it up later on. So here's a bit of a video. Hopefully this plays well enough. Are you able to see the video?
Yeah, that's fine.
Okay, great. So this is just a quick look at some of the team at Jet Propulsion Lab in Pasadena. Once they got the crew stage and the aeroshell put together, they took it up the hill and did a test to make and put it in the space simulator So simulated the flight to Mars, the environment that it would go to. Then they brought it back to the clean room. Then we started building up the rover, putting it all together. And then once you have it all built, then you also got to do all the environmental testing and functional testing on the rover itself, such as some of the first drives, doing some of the testing out each of the instruments, making sure that simulating the power system, making sure everything works properly. And once we can get all this together, then we have to pack it up on cargo airplanes and ship it to the launch site at Cape Canaveral, Florida. So I wanted to pause here for a moment to mention, it takes a lot of people to do this. This is just the people located at Jet Propulsion Lab about 1 year to launch. And we had about, at any one time, 500 to 600 people working on this. But, over time period, that's, 1,000 or more at JPL. But there were, many hundreds to 1,000 more people across the nation in the U.S., as well as, our partners overseas working on this. So it was a huge effort. And like all of you, everybody was impacted by the pandemic last year. Of all the challenges we could have envisioned, and we had a lot of challenges going to get to the point of shipping this to Florida. The shipping it to Florida was planned for February of last year. And so the pandemic started to hit right at this time. We were trying to get everything going to ship. And it took a huge effort to make sure that we could get it shipped, done safely. And then we had to transition the way our team was operating. About 80% of the team started working from home. Of course, we still needed people to work on site to do hands-on work. And the team that had to deploy to Florida to do what we call the assembly, test, and launch operations were, they had to spend months down there isolated from their families. Usually one of the perks of going to Cape Canaveral is, hey, you're on a beach location at work. You get to go to the beach all the time and hang out with your coworkers. Couldn't do that this time. So it was a very different experience, but the team definitely came through. So here we are at Kennedy Space Center in the processing facility there. And this is the stack of the spacecraft. The top is what we call a cruise stage. Then that conical start of the aeroshell. You see the rover in the aeroshell with its wheels tucked up. And then the bottom piece is the heat shield. That's the last piece of the aeroshell to protect the spacecraft as it's doing the entry into Martian atmosphere. Now, one of the things I mentioned, the pandemic, the team, there was no way they could have done it, on their own. They needed the support of not only their own families, but the broad communities, and particularly the frontline workers, the healthcare workers that were helping to keep people safe, take care of people who got sick. So shortly before, this was a last minute thing, shortly before we packed this thing up, the team designed a plate to be mounted on the rover with this symbol of the Earth. You see the symbol of the spacecraft launching, heading towards Mars, but supported by the healthcare community represented by the Serpent and the staff. And so this was bolted onto the side of the rover as a tribute to that community that really made it possible for us to do our jobs. So once it's all packed up, we got it loaded, put into the nose cone of the rocket. That's the launch vehicle fairing, comes together, seals the rocket in, load it on a giant tractor and roll it out to the launch pad. Then it's elevated, crane pulls it up to the top, integrated with the launch vehicle, and then we're ready to go. Now, a tradition that JPLers have is, and this started back in the early days of the Ranger program, when we were sending our first probes to the moon in the 60s. There had been failure after failure. And then one time, one of the guys had peanuts and was passing them around, and it was a successful mission. So it's been a tradition ever since at launches and landings that you share peanuts with your colleagues. Well, we couldn't share because of COVID, but we did find a way to, everybody had their individual packs and made sure they kept that tradition alive. And so we had a beautiful day, beautiful launch. on July 30th. So how did we decide where to go? Why Jezero Crater? We spent several years working with the broad science community, asking that question. For this, the objectives of the mission, where's the best place to go? And turns out Jezero Crater is a fantastic place. It once was a lake with an inflow channel and an outflow channel filled with water. And it has this ancient river delta structure. And here on Earth, those are excellent places where the flow out of sediments from the river into the body of water is a good place to collect potential organic remnants of biology. You know, if you go to the river down the road and scoop up a bunch of mud, you're going to find all kinds of life forms in there. So this would be this is a very good preserved delta. So this is what the science team was targeting. And that yellow circle is what we call the landing error ellipse. So that's somewhere within there, that's the targeting area that our entry, descent, and landing technology can get us within our target. Now, one thing new that we haven't ever done before is a new technique called terrain relative navigation. And we were able to use all the orbiting images that we've taken and create a map of that area. And the entry, descent, landing team was able to mark what areas were more hazardous than not, because science team, they want to land near those rock outcrops and interesting features, but to a landing person, that means danger. So it's this balance between how can you get as close to the good stuff for the scientists, yet stay in the safe areas so you can have a good day on landing. So this terrain relative navigation would be added a camera and a special computing element so that as we're coming down, we're taking pictures of the ground that we're headed towards, comparing that to the onboard map. And if it looked like we were heading towards a more dangerous area, we had a divert maneuver that we had to do anyway to get away from, once we detach from the parachute, we want to get away from the parachute so it doesn't fall on top of us. With Curiosity, it was just pre-programmed go north or one direction. For us, we were able to let the computer decide which direction it would go to be able, if it needed to direct us to a safer space. So here's an animation. If you aren't already familiar, this is animation of what the entry, descent, and landing technique is. We hit the atmosphere coming at about 12,000 miles an hour. So the aeroshell first slows us down, knocks off 10 of that, and a little bit over, almost twice the speed of sound. That's when the parachute is deployed. That slows us down even further to a couple hundred miles an hour. Then we detach from the parachute. The sky crane or descent stage rocket pack takes over and starts lowering us down. Once we get just a few meters above the surface, nylon ropes extend. As soon as the wheels touch down, cuts the cable, the descent stage flies away, and we are now safe on the surface. And this is how Curiosity landed. That was the first time we'd ever done that. And you can see how complicated this is. And hundreds of things have to go just right for that to work. So many of us wondered, did we just get lucky with Curiosity, or is, how close did we maybe come to not making it last time? And clearly it worked again. But when we did Curiosity, we have animations like this, but we had no visuals. There was no way to see how any of that system worked. So this time around, we added something special. We added some cameras. We added uplook cameras so that we could look at the parachute. Even though we sent many spacecraft to the surface of Mars and with parachutes, and they've always worked, we don't really know how well they worked. How well did that parachute inflate at supersonic speeds? So we really wanted to find out how that worked. And as soon as we started talking about doing that, we said, well, let's add some more cameras. Let's put a downlook camera from the sky crane looking at the rover, and from the rover looking up, and below the rover looking down. So, and we just used commercial off-the-shelf type cameras. We had to do it kind of quick and inexpensively. We couldn't interfere with it and do any harm to the rest of the design. So what I'm going to show you next is, this is the video. If many of you may have already seen some of this, but as we're coming down, this is the day. Here we have the deployment of that parachute. It worked beautifully. And take note of the pattern. I'm going to come back to the pattern of the parachute in a little while. So once that parachute slowed us down, we deploy the heat shield, and now two things are happening now. This is just the camera view of these off-the-shelf cameras showing us what's happening. But there's another camera that was doing that terrain relative navigation, taking snapshots of the ground as we're coming down and starting to think about, okay, am I coming down in a safe space or not? So once we started coming down, that terrain relative navigation said, okay, start going over here. It's a little safer spot. We started getting closer to the ground. You're going to see the rocket exhaust kicking up the dust as we get close to the surface. And then as the sky crane and the rover start to separate, we actually get to see ourselves landing on the surface of Mars. And if you look very carefully, once it touches down, the sky crane very quickly releases and flies off in this. It's kind of hard to see through all the smoke. But, and there it goes. So we were quite excited, as is pretty much everybody around the world who was watching. So here's a geological map of where we landed. The science team has divided the landing area into these squares that we call quadrants, and they've named each one for different national parks or preserves around the world that have similar geology to that area. And we landed in a place that the team had named Canyon de Chelly, which is a national park in Arizona. It's on Navajo reservation land. So the team has a theme. When they're in each quad, they will name features within that quad after objects or things in those national parks. So we're actually working with the Navajo Nation to come up with names in the Navajo language to give names to the different rocks as the team, rather than saying, oh, it's that, rock A or rock B, they have a tradition of giving other names. It makes it easier for the team to refer to things and talk to each other. To the right, that red and blue square, that shows you the terrain relative navigation map. The red areas are the danger areas, the blue areas are the safer areas. So you could see what it had to navigate through to find a nice safe spot right there. And we only landed about 1.7 kilometers away from the center of our landing ellipse target, which was kind of centered there close up to the delta. So right now the team is looking at where we're already on the move, scouting around a little bit for what we call an airfield for the helicopter demonstration. I'll say a little bit more about the helicopter, but they're considering going maybe a northern route to get to the delta, or maybe a southern route. Not sure which way to go yet. And we've named our touchdown point Octavia E. Butler Landing for an American science fiction author. She was a native of Pasadena and has written many stories that inspired the science and engineering team. So named that and dedicated it to her. So some of the first imagery, tons of images are now coming down. You can go to our website, mars.nasa.gov/Mars2020. Two places to look for images. There's the main imaging space where we're kind of putting up some of the highlights, but we also are pretty much putting out all the raw images as soon as they come in. So there's the raw images site that you can browse through. But these are a few highlights. This demonstrates the Mastcam Z camera and the zoom capability. You can see that rock. Some of the team was referring to it to the harbor seal informally once they landed. And if you could, by putting out all this data as quick as we can, the amateur community can take it and process it and do fun things with it. So this is actually someone out in the community, not science team, who put some of the panoramas together into this neat visualization. So if you were sitting on top of the rover looking around, this is what it would look like. You see off there in the distance, that's the crater rim. And we spent several days for the team was just looking at this rock and that rock. One of the things they would look at is, see right in front here is, see an area where it's a lighter space. That's where the rocket plumes came down and blew a lot of the dust off of the top of the rock. So it's very interesting for the team to be looking at sort of a cleaned off rock, and then they can compare it to some of the rocks that haven't been cleaned off. Now, this is the rear of the rover, and it's facing directly towards that near cliff. That is the edge of the river delta. So kind of that's our goal for where we want to head eventually. Over the past several days, they've been doing the commissioning of the rover, working out all the kinks of the science instruments, making sure they all function properly. And now we've started to exercise the robotic arm, check out the instruments on the turret. As of now, all these science instruments, mainly on the rover body, they've been given the thumbs up to do normal nominal operations. We're still doing the characterization and commissioning on the turret instruments, but those should be good to go pretty soon. And we started doing some drives, both to exercise the mobility system, and also start looking for where could we deploy the helicopter that we're carrying along with us. So I mentioned earlier, when you go to Mars, you want to make the best of it. And when we put out that call for experiments, we got something we didn't really intend, which was a proposal for sending this small rotorcraft. And the initial proposal was maybe it wasn't quite ready. So we said, well, tell you what, go off and study it. We gave them a little bit of funding to keep doing technology development. And if they could get to the point where it made sense, then they could come back and maybe have a chance to get on the mission. And that's exactly what happened. They did a lot of quick development and testing, and designed a system that could actually fly in the very thin atmosphere of Mars. Martian atmosphere is about 1% as dense, as thick as here on Earth. So that's why you have to have very large rotors. It has to be extremely lightweight. So they designed a way for this to fit underneath the rover. And so we put it there, covered by a debris shield. We didn't want it getting hit by all the rocks and dust we blew up as we landed. We had to have a deployment system to deploy it upright. So we're looking for a nice flat area to deploy this helicopter in the next within the next month. And then the rover will back away about 100 meters and relay the commands to the helicopter to do a couple of test flights. We're planning 5 test flights. This is just a technology demonstration to really see if this is even possible. Might work, might not. It's a high risk, high reward type of activity. And so the idea is that if we can, learn how to fly on Mars with this tech demo, we can use that to potentially design bigger aerial platforms that might be able to take actual science instrument. This one only carries 2 small cameras, like your cell phone camera, and no particular science involved in it, but just a visual camera to see what you can see from the helicopter. And once its flights are completed, then its mission is done, and the rover will continue on its way for the sampling campaign. So we're on the ground now. I mentioned the sample return campaign, the future missions, but up next is ESA with the ExoMars rover. And this is something that NASA is also collaborating with. The rover itself actually was, a large part of it was built there in the UK. Prime contractor Airbus at the Stevenage facility integrated the rover. And we at the NASA side are providing key components to the premier astrobiology instrument on the ExoMars rover. It's called the MOMA instruments, Mars Organic Analyzer. It's a German-led instrument with French and US contributions. And this is set to launch at the next Mars launch opportunity in 22. Now, coming back to the parachute, I mentioned this pattern. When I first saw this, I said, now, wait a minute. You know, I've seen parachutes with, you know, a pattern because you like to be able to, you know, use that to understand the inflation, but this seemed pretty unusual. And it made me wonder if JPL snuck something in again, because on Curiosity, they, on the wheels, they put a certain pattern of holes on it that were a series of dots and dashes, so that every time it rolled on the surface of Mars, it kept printing out on the surface of Mars in Morse code, JPL, JPL, JPL. And that was something that kind of a neat secret they did. We knew that wasn't going to happen this time because our wheels are very different. But here in the pattern of the parachute is encoded in 7-bit binary letters is JPL's motto, dare mighty things. And then on the very edge is the lat-long coordinates of the location of JPL at Pasadena. So you know, they did sneak another secret in there for us, but I think it's a great message and a great motto for all of us to always try to dare mighty things. So I've talked for quite a while. You guys didn't interrupt me with any questions, so certainly can answer any you may have, but definitely want to encourage you to follow us. Again, check us out, mars.nasa.gov, Mars 2020. You can also follow us on social media and keep up with the mission. There's a lot of exciting things to come.
George, thank you so much for that. We did have a number of questions come in, but you were flowing so beautifully and marvelously. I really didn't have it in my heart to interrupt you. But I'd like to take you through some of the questions that we've had. And in the meantime, if people want to add more questions into the chat, I shall look through them. So here's a great one. We have Perseverance picking up soil samples and for the moment just dropping them here and there. And the Fetch rover is going to pick them up and take them to the return craft. Well, we know that the weather on Mars is not always that static. So what should happen if we get dust storms and the sample tubes get covered over? Is there any kind of homing system built in?
No, because we don't really need it. From the other landers that we've sent, like Spirit, Opportunity, Phoenix, Insight, Curiosity, and we've been able to observe, you know, through many seasons and many global dust storms, what type of dust deposition you're going to get. Now, you know, it certainly may vary by location, but with this is a key question. Yeah, we asked as we were designing the system, but it turns out that on the time scale that, you know, we're going to be going back to getting within the next 10 years, there's not enough deposition to be worried about it covering them up where we aren't going to see it. You know, in fact, if you look at like some of the long-lived landers, like the Spirit and Opportunity, you know, their solar panels got dust on it, but it wasn't enough that, you know, you get a thick layer or anything. And also, you ended up having dust devils come by and blowing it off. That's the way Spirit and Opportunity were able to survive so much longer than their original design was. We actually had these cleaning events. And we will know very well, you know, just by the location of the rover, we know where we are. We'll know, you know, within a meter or two where these things are, and the Fetch rover can go find them. Okay, yeah, because of course you are going to log the locations of each one as it's cached anyway. As for Spirit and Opportunity, this was something I actually put to Steve Squires, who is the principal investigator.
as to whether a future rover that relied on solar panels might actually have motors to lift the panels up so that any dust on them could slide off, and you might do that periodically. We've actually had a question about how the rovers were powered, and I've said they are radioisotope thermal generators. Do you want to add anything to that?
Yeah,
How long are they expected to last?
Right. We use the radioisotope thermal electric generators, RTGs for short. You know, these are passive devices that NASA and the US government have used for 40, 50 years on space flight missions. You know, Russia has also flown some of their variants of those types of things. They even went to the moon with the astronauts, with the Apollo astronauts.
Yes.
And so they're very reliable. So, you know, no moving parts, which is great for us, right? And so we use small pellets of plutonium-238 mixture. It's called plutonium dioxide. The pellets are about the size of a large marshmallow, kind of used for roasting over a campfire. And we package several of those in some different layers of containment and protective material, carbon fiber, and iridium clads, and stack enough of them together. So we have like 36 of these pellets that generate the heat. And around that stack is thermocouples that, so that the temperature gradient between, you know, the exterior and the interior heat creates the electric flow. And it's not, you know, it's not the most efficient conversion of electricity, but it's very simple. So we can get about 110 watts at the beginning of life out of the RTG, and that's plenty to run our system. And we use that, we can both draw direct current as we're going and charge our battery. So there's also batteries on board the vehicle that we're charging. And this allows us to operate. I mean, you could operate day or night, but in truth, you really only operate in the day because you don't want to have to expend a lot of energy for heaters and those sorts of things at night. Plus, doesn't help taking images when you know it's dark. So that doesn't help you.
Okay, that's good. Anne asked about the mast cam. If anything happens to the mast, she says, are there backup cameras? I mean, actually, it's covered in cameras, but
it really is. We have, I think when we launched, all told, you could count 23 cameras on this spacecraft. Now, some of those were the entry, descent, landing cameras. So some of those were lost, you know, when the descent stage and the back shell completed their activities. But so I think we have maybe 19 left all over. But, you know, some are, you know, not big cameras like Mastcam, but the main thing, another big improvement from Curiosity was we upgraded what we call all of our engineering cameras. So there's, if you go on our website, you'll see images from what's called NavCam, navigation camera, or HazCam, hazard camera. And these are all upgraded, whereas Curiosity, they're all black and white. Now they're all color, higher resolution. And in fact, I mean, just those are really good to do science with. So yeah, thankfully, have full confidence Mastcam is going to do great. Its predecessors have all well survived their missions. So I'm sure this one will do just as well. But you know, if you know, heaven forbid, you know, that didn't happen. We've got others that we can still do our mission.
Okay. Theo, one of our young observers this evening, has said, is the rover covered in something? He's said somewhat like spacesuits for protection against heat. I mean, it's actually fairly cold on Mars, but there's various kinds of protection that you do need.
Well, you know, there's not like a, you know, spacesuit material like we would need for humans, and it's pretty much just, you know, the rover is built out of aluminum honestly, aluminum and titanium, depending on the component of what we need. You know, if it needs to be lightweight and stronger, like the sample tubes are titanium. But majority of the rover, you know, bulk mechanical body is, you know, a lot of aluminum. It's hogged out of single pieces like the wheels, and it's more. We don't really have to worry about radiation so much because the electronics are radiation hardened electronics. It's really the temperature issues. And coming back to the RTGs, not only do they give us electricity, but they give a lot of waste heat. So we actually have a fluid pump going through the rover, picking up the waste heat from the RTG, pumping it through the body and around the electronic box to help keep the rover warm. So that way we don't have to use the electric power to generate electric heaters. Mostly those are for like any place where we have an actuator for our motor, say for the wheels or for the robotic arm or the instruments at the end of the arm. You know, those are hanging out in the breeze, getting really cold. So you have to use electric heaters for those.
Okay. Right. Jeff asked about measures that were taken to prevent Earth contamination on Mars. I mean, this is a basic thing. When you're searching for life somewhere, you don't want to find the life that you've taken with you.
Exactly right. And so because of that, there has been long since early part of the space age, there was actually international collaboration on trying to set out a set of principles of what we call planetary protection. For any place that we would go explore, you want to make sure that you're not contaminating the place you want to go study. So we have the Committee on Space Research via the United Nations. All the nations get together, talk about the best principles and guidance. And so, you know, we at NASA pretty much follow those same guidelines. And this is the cleanest spacecraft we have ever sent anywhere. But there's two dimensions to the cleanliness. One is there's broad levels of cleanliness that you want the whole spacecraft to be. And that's kind of our normals cleanliness. You saw the staff in the video wearing what we call the bunny suits, the white suits. But there was a whole nother level of cleanliness for the sample hardware. So pieces like the drill bits and the sample tubes, we call these sample intimate hardware. This stuff had to be even extra clean. We had what we call a level 1 requirement that there could be less than one earthly viable organism on these components. So basically 0. More sterile than any surgical type environment. So we actually had to invent new ways of doing cleaning and keeping them clean. In fact, so like I mentioned, this is a 3D model, but the gold color is actually part of that contamination control program. It's the real ones are coated in titanium nitride, and that helps us. It helps with the cleaning. It also helps prevent organic molecules from adhering out of the air and adhering to some of this material. They're cooked, they're baked out, kept sealed through the launch, and we spent a lot of effort trying to develop the right way to keep these things clean. And so that, yeah, exactly, these samples that we bring back, we want to have nothing on them. But another thing we did was 5 of these tubes actually have something in them. It's what we call witness material. We filled them with some material, and before we do some sampling, we'll actually take one of these tubes, go through the entire process of up until you put it up to a rock that you might otherwise do. And that way, if there is any contamination coming off the rover, that material will potentially collect it. But we will also seal this up, leave it on the surface. And so in addition to some of the rock samples, we'll be bringing these witness tubes home. So we have that comparison. if we can find any contamination in the witness tube, then we know to discount it when we're studying the samples.
Okay, yeah, that's right. And the other half of the question is, of course, about bringing the samples back to Earth and what happens there. Now, with the first 3 Apollo landings, the astronauts went into quarantine in the lunar receiving laboratory, and they stayed there, I think, 21 days, while all kinds of tests were done to see if there could possibly be any kind of contamination brought back from the moon. And I mean, is the LRL still there? And is that what's going to be used, or is there a new facility?
It would be something different, but the basic concept applies, right? When you have something coming back from a location, and this is part of those planetary protection principles, we refer to it as, the part I talked about before is what we call forward contamination.
Yeah, this is.
Then we got to worry about the backward contamination.
Yeah.
And so if we are bringing things back to Earth that, there might be any possibility that there might be some type of biological material. What we want to do, even though there's no evidence that there is anything harmful or at all alive at Mars, we're going to treat it as if there might be, and we will treat everything as if it is hazardous until proven otherwise. So the containers that, many layers of containment. One, the tubes themselves will be hermetically sealed. Then there'll be that container will be completely sealed, that all the tubes are in. Then that container will be inside yet another container that goes inside the Earth entry vehicle, which is yet another container. And all of these sealed so that when they land on Earth, then we'll be able to pick up the Earth entry vehicle, and then you take it to a special facility that is yet to be defined. That would be a containment facility, and that's when you start to open up those different layers. And the containment facility is actually a receiving facility. It has 2 purposes. One is, the more concerning thing is, make sure no Earth contamination gets in. We went to all that trouble to make sure we have pristine samples. You don't want to introduce more contamination on Earth. And then the other way too is, if there is anything hazardous, you want to make sure it doesn't, get out in the Earth environment. And there would be protocols to do testing, similar to what we did with Apollo. Once they determined there was no issues, if we go through those protocols and determine it's safe, then the samples could be able to be released beyond the facility. But the idea is that even until then, we would have the science instrumentation at the facility to be able to do in situ studies on them.
Okay, thank you. Richard's asked about the MOXIE experiment, that if you're extracting oxygen from the air, he said you're going to leave carbon monoxide back, and he's basically asking you if this is a problem. You've got something that's poisonous, but then we don't have anybody there who's breathing it at the moment, at least anyway.
Yeah, I mean, for our experiment, of course, I mean, this is very, very small amounts for, comparatively to the atmosphere that we're going to be generating. But it's a good point. If whatever type of system, whether it's this technology or maybe a different type of oxygen generation, when humans, eventually go there, you'd need to manage that. What do you do with carbon monoxide that you get? There's some other thinking of, okay, that could also be a resource. Maybe you are bringing some other sort of feedstock of other materials that you can then mix and create other resources that a human system might need, fuel or whatever it is.
Okay. Another question from Theo. What are the parachutes made of? He was worried about them perhaps getting burnt during some stage of the re-entry process.
Yeah. Forget, I can't recall the exact material, but it's a standard parachute material made by, same types of manufacturers that make, parachutes here on Earth. These are definitely a bit more specialized. It's largely in the design of where the support portions are on the parachute, so that can be inflated at supersonic speeds. And we don't have to worry about a burn up because we've already come through the atmosphere. It's the aeroshell that slows us down from the hypersonic speeds of when we're hitting the atmosphere down to supersonic speed. So we're only going, less than Mach 2 when those things deploy.
Yeah. I must say that Theo has written this pretty amazing note. He says, "This is the most interesting Zoom I have ever been on. I'm 13 and done school on Zoom, and I've never looked forward to and enjoy a Zoom as much as today." So we're so pleased that that he has enjoyed it so much. I hope you're still up and watching, Theo.
I will tell you, this is definitely, these types of Zooms are much more enjoyable for me as opposed to the typical Zoom meetings we have in our day-to-day jobs, right? How many video cons can we have? But, being able to talk about, the exciting things we're doing and particularly sharing it with, the broader public, that's why we do this, right?
Yes.
Create discoveries, to share what we're doing, to inspire, like I said, dare mighty things, so Theo, this is your interest, go for it, or whatever the interest is, maybe, you're interested in art or, business or what have you, find your passion and go do it. And
okay, Jeffrey has asked that there seem to be some bits that seem to break off when the parachute opened. Was that any concern, or was it just extraneous wrapping that was meant to go off?
Some of it just had to do with the way the chute was packaged. There might have even been, I remember the EDL team did mention something that came off. It might have been the cap or a cover of the camera system, or maybe even been a component of the camera system, not sure. But it wasn't anything that they were too worried about.
Okay.
I'm sure they'll look at it and find out, if indeed it was, and if that means anything for future missions.
Okay. So Paul has sent this message. It says, "I believe Curiosity ran for much longer than expected." Well, of course, Spirit and Opportunity did. I mean, their design brief was 3 months, and 14 years is considerably longer than that. So as Curiosity ran for longer than expected, I mean, that I think its design mission was meant to be a year, and it's still going from 2012, isn't it? He said, "What did that do to successive NASA budgets? I have a vision of the bean counter saying, 'What, another year?'"
So yes, there are always those, we call those programmatic conversations. But so let's distinguish a couple of things. One is we talk about what's the design. When we design these rovers, we do the testing to qualify them for a certain amount of time necessary to achieve the objectives of the mission, right? And so yes, Curiosity was designed for 1 Mars year. That's 2 Earth years approximately.
Yeah.
Right. And we wanted to, I mean, for sampling, you might say, oh, we want more time, but part of why we were using the Curiosity design was it worked well. And we wanted to, we knew we had a lot of other new things we had to do. The sample caching system was going to be a brand new thing, very challenging. All these new instruments, very challenging. We wanted to reduce the number of new things and new miracles we had to pull off. So utilizing the heritage of Curiosity as much as we could is what we did.
Yeah.
That also helped save us costs.
Of
So
course.
we said Perseverance is also going to have a design. I mean, the requirement is 1 Mars year, and you have to plan to be able to do your mission in 1 Mars year and qualify. Now, the team, when they did that, they ended up qualifying it for 1.5 Mars years. So we got a little bit of margin too. But as we know, with many other missions, my screen is going blank. Hopefully I'm still talking.
Yes.
Okay.
Yeah.
We do plan budgetarily for what's called extended missions. So we do have some of that looking forward, and actually about every 2 years in our portfolio of space science missions, they all go through what we call it a senior review, where we have review panels. It's kind of like a peer review panel of saying, all right, this mission is still alive. Well, is the science it's doing really still a priority? Or are there other priorities that we need to better put our resources towards? And so we go through that process, and most of the time, yes, indeed, a really good viable asset is better than either none or whatever the next best thing is. But sometimes you do have to make those trade-offs.
Yeah, yeah, and of course it's much cheaper to have a craft and extend its life than it is to design, build, and send off a brand new one.
Yeah, sometimes, but then at the same time, you always get new questions, right? So and you can't update your existing spacecraft to ask different questions. They're designed for one thing, and that's why bringing samples home is such a big goal, because while we put all the greatest things we can put on Perseverance, it is what it is, and it can only detect what it can detect. But when we get samples here on Earth, then we can apply all the kinds of techniques across all the worlds, all the labs around the world, and also some that haven't even been invented yet.
Yeah.
The Apollo samples we are still analyzing and still learning from.
Yeah. Yeah. Okay. Dominic asks, have you thought of trying to grow extremophile bacteria from Earth on Mars?
That would
I'm
violate
sure
planetary protection.
Yes, yes.
People talk about that, would you want to bring an experiment that was like a greenhouse experiment or something?
Yeah. Well, perhaps
we're not at that point.
As and when humans get there, perhaps. Are there? So John now asks, are there any thoughts about looking at the purely geological features of Mars to look at the history? He says, I had in mind the huge volcanoes and Valles Marineris.
Oh yeah, that's that really crosses everything we do, really. Many of the missions we send are very multidisciplinary, right? And geology is often really at the heart, both from looking from orbit, and then most of our surface missions, have some sort of, geology component. And, as you see on Perseverance, we have to understand that context to help inform looking for the sample that we want to go to. So that, that's where the RIMPAX ground penetrating radar is going to be sort of a neat new advance. We've always been able to see from the surface, but we haven't been able to see what's underneath. And sometimes you have different geologic units. Understanding how those are it gives you a much greater dimension of understanding the different units and where you might want to go to find some samples.
Okay, Nigel asks, what are the biggest forward risks facing the mission?
Good question. Okay, so far everything has been going very smoothly, pretty much. All our systems are operating. Kind of the next, aside from the helicopter experiment, which it really is an experiment. If I mentioned it's high risk, high reward. If it doesn't work, that's kind of okay. That doesn't affect the rest of the mission. The other key thing coming up is commissioning the sample caching system. This is the most complex robotic system we've ever sent. to anywhere in the solar system. And seeing that, I mean, you know, the robotic arm itself is working out okay, but now we need to test the drill. We need to test the internal robotic arm, and you know, doing some of those first things. And this will be, you know, probably a couple months from now till we get to that point of trying to do some of the first sampling. That's kind of the next thing I'm anxiously awaiting. But you know, other than that, once we get the full mission commissioned and characterized, and everything looks good, it's really more a matter of you know, being careful with this new asset we have on the surface. And you know, fortunately, we program in fault protection and that sort of thing. So if something kind of goes wrong, or we send an incorrect command, the rover's smart enough to say, you know, whoa, I shouldn't do that. Or, you know, say we tell it to drive in a certain way, and it reaches an obstacle and can't get around it, knows it can autonomously, you know, stop and call for help. So, you know, beyond that, the next big risk is, you know, designing and implementing the next couple missions for the sample return, because those are definitely going to be big challenges.
Okay. Here's a question from Ange. What about medical needs for any time length being on Mars? How would that be planned for if someone needed surgery, for example? Well, on Skylab, the American space station launched in 1973. The crews on there who stayed for up to 3 months at a time were actually trained on how to fill and remove teeth under emergency conditions. But beyond that, and when you're not just in Earth orbit, but 200 million miles away.
Yep. You know, right now we have the International Space Station with, you know, it's been permanently crewed for, you know, 20 years.
20 years. Yes.
And so, you know, and we've had crew that have been up there for a year at a time.
Yes.
So, you know, you need to have that, you know, they've got training for certain, you know, levels of, you know, healthcare and that sorts of things. But, you know, that's a little bit different. You know, if you had a, you know, an urgent chronic issue, you know, coming back home to Earth is, you know, a couple days, right? Planning. So now, you know, if you have something super urgent, you know, somebody's, you know, bleeding profusely or something, that you got to deal with right on right then. But you know, things like, you know, say you get appendicitis or something like that. Well, all right, you know, come home and we take care of it. But yeah, going to Mars, there's no quick return to Earth. So you know, beyond just trying to figure out how can humans live and work in outer space, given the harsh environment, the microgravity, the radiation environment, you know, how do you plan for things like that? You're going to have to plan to take everything with you, both in terms of supplies and skills. So, you know, you can expect you're going to have Dr. McCoy with you, or something. Sorry for younger generation if you don't know Dr. McCoy. 2
doctors. You need backup in case the doctor has a problem, of course. I mean, I pre-COVID, I used to go out to schools all over the country presenting space workshops, and the major one was called Mission to Mars, where we would start off by building and launching rockets vaguely in the direction of Mars, and then they would design landers and so forth. And in discussing all of this, I said that when we send humans to Mars, it's not just pilots, not sort of career astronauts as well, but we're going to need the people who can actually keep people alive and keep everything going when we get there. So you're going to need doctors, you're going to need engineers, mechanics, and those sort of people. There's a whole range of skills that people will need when they go to Mars.
Absolutely. And
yeah,
what size crew does that mean? And then, well, okay, and definitely the more crew you have, the bigger flight system you got to have, and then
yeah.
all the implications for that. So
So
yeah,
everybody's going to need to be multi-skilled, of course.
yeah,
Yeah.
absolutely. Or
Okay.
and easily trained too, right? So that
Yes.
if you gotta send up some new training to learn a new skill, you have to be able to do that too. Jacks of all trades.
Yes. Yes. Absolutely. So, oh, here's one that comes back to cost control. Who has responsibility for delivering within budget? And what if they fail? Haha.
Um,
Well,
Many different levels of responsibility. Of course, at our we call it our implementing centers. So in this case, the Jet Propulsion Lab in California. We give them a certain budget. There's an agreement on a certain budget, and we say, all right, you have to implement to that budget. They have some reserves. We hold a little bit of extra reserves at headquarters. But yeah, it's not uncommon that in developing, especially large, complex missions like this, that you do end up, um, sometimes needing additional resources, and then you have to make those choices of, are we able to get more resources to keep going the way we planned, or do we need to change the plan and what we call descope, shrink our ambitions? Sometimes you have to do what we call termination reviews on science instruments. For example, if they are, not coming in on budget, you have to really look at it and see, okay, is this worth it or not? And we were very, I feel very fortunate in that the mission that Perseverance has, it's high. It was rated. Our National Academy of Sciences every 10 years does an assessment of the broad planetary science goals. And right before we started this mission, these mission objectives were rated the highest priority, large class planetary missions. So it was a high priority in the science community. We had broad support in the executive branch of the government, the legislative branch. So we were able to keep going and do what we needed to do.
okay. Okay. We have just two more questions at, at the moment. Dominic asked, what do you think about the commercialization of the space industry, Rocket Lab, SpaceX, etc.? I had to say, when I get asked this question, my reply is that NASA really is an innovator and not an operator. And on that basis, the commercial launching of space is what should be happening. Do you agree with that?
Yeah, I think that's definitely the direction the agency is headed. And in fact, the past 10 years, as you've seen, particularly with our commercial crew program, now we have a couple of different vendors, working on, commercial crew and cargo services. And that is so far, paying out. And, you'd like to see that expand, right? You'd like for NASA and the federal side of things to be trying to always push the frontier and push the edge, and either develop capabilities or technologies to then transfer or disseminate to the industrial sector, so that there can now be private enterprise to be generated and take that on and offer it not just for government use but for private use. And so yeah, definitely, the more we can see of that, I think the better. And I'd love to see that kind of thing continue, particularly with Mars. Can we start getting some non-traditional actors in the game of Mars exploration that might be able to leverage what we as nations can do?
Yeah. Okay. And so let's finish off with this one. If ancient or even current life is found on Mars, will it be announced immediately, or will there be a wait? Now, I will say there will at least be a wait until we have a second positive result. Don't base everything on a single data point.
Right. So, you know, detecting life is extremely difficult. You know, even here on Earth, you know, if you go out to what we call Mars analog sites in environments that have some similarities to Mars or whatever, if you're trying to like going out into the Australian outback, trying to find those stromatolites can be actually quite difficult. There's no such thing as a tricorder of hey, there's life. And we have these various instruments that are seeking for just pieces of the puzzle. So it's definitely a searching through a lot of different evidence, trying to then put that picture together of all that evidence that could then lead you to say, hey, yeah, maybe that's it. So I unless we saw something just blatantly obvious, I mean, I'd love to have that problem. And you can imagine, but even then I would suspect, the science team would say, well, here's what we found. It really looks like XYZ, but we can't definitively know until this condition or that condition. Our approach is being open with the community, open to the public. That's why we, particularly our imagery, we're putting raw imagery out pretty much instantaneously. The other science data gets put on a system called the Planetary Data System, for the broader community to be able to utilize. If we had a discovery that big, it wouldn't stay secret. You can imagine.
No, I'm sure. I'm sure. Well, what can I say? I mean, this has been an absolutely incredible evening. The accolades that have been pouring in on the chat have been really amazing. I'm going to copy the whole lot, and we'll send some notes through to you. So,
sure thing.
I mean, if nothing else, you can say to your manager, looks like I did a good job that night, because you really have. I mean, this has been heaven for me. I have been a space buff for, heck, I've been giving talks on space for over 50 years. So, since I was knee high to a rover. And I need to mention that when Perseverance landed on Mars, then so did I. This was my 7th flight to Mars, but my granddaughter, who will be 12 years old in a couple of months and is really keen on science, I signed her up to it as well, which is appropriate with Monday being International Women's Day. For her, it was Interplanetary Women's Day. She's the only person in her school who's on Mars. And I look forward to her being on a lot of other flights to come. George, thank you. Saying thank you is just totally inadequate. But everyone here has so enjoyed following what you've told us about this remarkable mission, and we're extremely grateful to you. Thank you very much.
Thank you all. And I have to say, even those of I mentioned the thousands of people that worked on this, and one of the things that we always get energized by is when we're able to engage with the public, and particularly groups like yours that have a keen interest in science and space. And so thank you all for inviting me to join and share what we're doing. And it's yeah, it's been a joy. So thank you again.
It's fantastic. And I can tell you, Alan and I were just a little bit worried early on when the numbers started keep going up, and we did wonder, just literally 2 more and we would have had to have increased the Zoom license to cater for that. It was touch and go, wasn't it, Alan?
Absolutely. Can I say thank you very much indeed, ladies and gentlemen, for coming along to what has proven to be a fantastic evening. I would like to say thank you to everyone who's made it possible, particularly to our speakers, to Martin and to George for providing the core of the evening, and especially to Jerry for finding such wonderful speakers. And I also want to say thank you to all the rest of the committee who make it possible. There's an awful lot of work goes on in the background so that we can put these presentations on. We're only amateurs, we're all learning, and we're hopefully getting better all the time. Let me tell you briefly that the next meeting is on Wednesday, April the 14th, when we can look forward to hearing about the 60th anniversary of human space exploration. The talk is going to be given by our own Jerry Stone, so it promises to be yet another interesting, exciting evening, which I'm sure you're all going to look forward to. Shall we let Jerry tell us a little bit?
Well, no. It's just that April the 12th is known as Yuri's Night. It's the anniversary of Yuri Gagarin becoming the first person in space. And our meeting is just 2 days after that. So this will be our celebration of the diamond anniversary of man in space. But I can tell you there will be a bonus. Alan doesn't know about this.
Oh, no.
I'm preparing something for World Space Week, which takes place actually later in the year, but I'm going to use it for this. It's a word search on space exploration. And so we will send that out with the newsletter. And as with all of my word searches, when you've found all of the hidden words, the letters that are left over will spell out a message which you can send to me. So you have that to look forward to. Closer to that, if I can just mention, this Sunday, I'm co-hosting a webinar entitled Development of Mars, the Asteroids and Beyond. And I think the simplest thing is anyone interested in that, email me at Jerry with a J, jerry.stone2001@gmail.com. So it's Sunday afternoon, it's free, and there we go, more exploration.
Okay, thank you very much indeed, Jerry. I'm sure that's going to be another fascinating talk as well. Well, folks, that's the end of our talks for the evening. It's been wonderful to see you here. It's wonderful to be worried that we're going to go over the limit for our Zoom license. And I look forward to seeing you all again, April the 14th. Until then, thanks for coming. Cheerio to all of you. Bye-bye now.